Mute. Hello.
Hello, Adish.
Hello. I'm unable to start the video.
Um, you, your camera is below. You can.
Yes, I just sent you a note on Slack. So it says unable to start video. You can't start video because host has stopped it. Maybe you need to give me permission to start the video.
Okay, I will try to check the permission, but maybe we can start. Okay, and I will check if we can allow permission.
Okay, yeah, because I think would be useful to have video so I can,
Okay.
explain certain things in a better way.
Okay.
Yeah. Hello, Maria.
Yes. Yes.
Yeah. Okay. I guess my video should be on now. Can you see it
Yes.
on your screen?
Yes. Yes.
Okay,
Yes.
great. And my voice is clear as well.
Yes. Everything is clear.
And so I guess the screen is shared, right? So I can get started.
Yes. Yes. Right.
Okay, great. So welcome everyone, all the participants who are attending this lecture. It's my great pleasure to be giving this lecture. Last year, I also attended Lviv Data Science Summer School back in 2019 when it was a physical school. And I'm happy to participate again in this online version of this school. So just a bit of my background. I am a faculty member at Max Planck Institute for Software Systems located in Saarbrücken in Germany. And the fact that we can't really interact face to face, right? So it creates a bit of a challenge. So I would really encourage all the participants to pose their questions on Slido. I have that on my side, so I can see your questions, and most of the questions we can handle at the end of the talk lecture. But if there would be certain questions which require some more clarity in the beginning, so I can take some of those questions as I'm kind of going through these lectures, right? So let's get started. And I guess the very first question, which is there, the difference between learning and teaching. So thanks for asking this question, because that's basically my first slide here. So just 1 minute. Yeah, so that's basically how I'm going to actually start the lecture, because all of you have heard about, machine learning. Everybody knows about machine learning, and perhaps not many of you have heard about this topic about machine teaching, right? So what exactly is the difference? How these two fields are different in terms of applications, how they're different in terms of formalism, right? So I think that's one of the very important things that you need to understand from this lecture, right? So I'm gonna basically start from here. Just a moment. So good. So let's start with what machine learning is, right? So as a very high level overview of how machine learning works, right? As you can see, basically here, the focus is on designing a learning algorithm which could extract some knowledge or rules from training data. So let's say, the goal is to develop a classifier which can, in future, detect what kind of animal species is in the image. Right? So the typical process is you're given some training data in terms of labeled images along with their labels. You would run some kind of a learning algorithm which can efficiently process this data, and then you would output a hypothesis, for instance, a trained neural network, right, which you could apply in future on unseen images, right? So the main focus here is really on the learner, right? So that's basically about designing learning algorithm. Now in teaching, the process is somewhat different. Here, the focus is on designing a teaching algorithm. And what does that actually mean, right? So here, let's say the goal is to teach a learner to be able to efficiently classify images, right? So what you have as input into the teacher algorithm. So here the teacher is basically an algorithm. You have a model of the learner. So you basically know how a learner is processing the data, and you have some target hypothesis, target decision boundary or a policy that you want to teach to this learner, right? So you can see the input is very different to this teaching algorithm, a model of the learner and some target. And what would be the output of this is basically some optimal teaching data, right? Now, what does optimal teaching data mean? For instance, it could mean teaching data of minimal size, right? In when we are teaching image classification, it could mean a minimal curriculum, smallest curriculum of optimized curriculum of tasks that students should do to be able to learn some, gain some knowledge, right? So as basically this is one slide that I think is very important to have a takeaway message. Now you might be wondering where does this kind of machine teaching formalism actually make sense? So that brings me to the next slide. Why do we want to study this inverse problem of learning, right? So teaching is somewhat like an inverse problem, as you can see in that slide. So one very natural application where you want to study a machine teaching way of thinking about problems is adversarial settings of what is known as training set poisoning attacks. Okay, so what is happening in training set attacks? Basically, you have a learning agent, which could be, let's say, a banking system or a recommendation system. And then you have some hacker who is, in this case, playing the role of a teacher, right? So you're designing, let's say, a hacking algorithm to attack that some system. In this case, what hacker would like to do is uh, change the training data. So for instance, doing some kind of a clickbait or click poisoning attack to end up have the recommendation system end up in some malicious state, right? So, and here, so that hacker is not kind of detected by the system, you want to make these minimal perturbations into that training data, right? So one more important thing to note here is we are talking about here training set attacks, not the test time attacks. So most of you are probably more familiar with test time attacks where the network has already been trained. This is a training time attack. So it's the training time attack, which is essentially the machine teaching way of thinking about the problem. Okay. Now, on a bit more positive side, from an application point of view, another important application settings are coming from educational domain, right? So in this case, you have a human learner who is basically the learning agent or basic here, right? And the teacher would be an intelligent tutoring system, for instance, who's basically designing the curriculum of courses, or it could be some educational simulator and other settings where basically we are trying to convey some knowledge to these human learners, right? In both these settings, as you can now see, your focus is on designing the teaching algorithm. The input to that teaching algorithm is some kind of a learner model, which could be a machine model, or it could be a human learner model. And then you have some H star target, which is kind of the final knowledge that you want to transfer, right? And the output of this teaching algorithm would be some kind of optimal perturbations to the training data, or it could be some optimized curriculum of data points or tasks that you should give to the student. Okay. So let me go a bit more deeper into some of these applications just to set up the context and give you a better overview of what kind of applications we are talking about, right? So now this is an application everybody is familiar with, right? Now there has been astronomical growth of students taking online courses, and thousands of courses are offered nowadays, right? So one of the biggest challenge with these platforms is that there is a huge dropout of students. Basically, they enroll and then they are basically not feeling engaged and they stop taking those courses, right? So these platforms serve a good purpose of delivering content, but they don't serve a very good purpose of optimizing the content for the students, providing some personalization or able to do some personalized interventions when student is stuck doing certain activity, right? And that's kind of the thing we would like to do. What a human tutor would do, that's the thing we would like to do in this kind of intelligent tutoring systems, right? Another application, for instance, these cognitive tutors, which are very popular for high school algebra or mathematical problems. So assessment is one such platform with over millions of problems solved per year by high school students, right? So these are the problems of finding area of a triangle, applying some congruence rules and so on. Right. And another very popular application that has gained a lot of attention in last few years is teaching kids or novice programmers how to program using some kind of visual programming. Right. So Hour of Code is one popular platform. I encourage you to check it out. It's on code.org. Millions of students have been using this in the last few years. There's been an astronomical growth here, and over zero point 0.8 billion hours of coding activity has been spent by students on these platforms, right? And again, if you go to these platforms, you would actually notice that you would be presented with a bunch of tasks which you can go and solve. But there is no notion of helping the student when they are unable to solve a task, or telling them this is the right task for you to do next based on some kind of knowledge that they have, right? And another application, is inspired from educational simulators. For instance, simulators for car driving, where you might want to train something in a simulator to acquire knowledge in a safe way. So I'm going to play this one video just to give you a context. So this is, for instance, educational simulator for surgical training developed by one of the companies in Zurich, Watchamed, right? So they manufacture a lot of these high-end medical simulators. You can go and visit their website. They have a lot of these videos about different kind of simulators. Right? And here you can see that these simulators would allow you to perform different kind of tasks. And the hope is that basically medical students can acquire knowledge through these simulators and then apply that in the real world. Okay. Um, and again, in these simulators, the key challenge is really that right now in state of the art, normally you need some medical expert to be sitting next to the students so that they can provide feedback, right? And in ideal case, what we would like is that there is an intelligent tutoring system or a teaching algorithm behind these simulators, which can do kind of nice curriculum and nice interventions. Another application everybody is familiar with, right? So language learning platforms have started about from 70s and have really gained a lot of attention with Duolingo and other recent apps. These apps are basically based on an algorithm of how to repeat certain cards based on how students are performing on those cards, right? These algorithms have been over a century old. However, we still don't have a very good understanding of what is an optimal curriculum of displaying these cards. And we'll see some of the questions in our research in part third of the lecture, right? How we can design more optimized algorithms to present this display of cards to the students so that they can learn this in a better way, right? And then another application domain kind of is somewhat different. You might not immediately think of this in an educational setting, but something that we have been working a lot in our research group in the past is inspired from this biodiversity citizen science project for biodiversity monitoring. For instance, birds are an excellent indicator of health of the ecosystem, and as of now, about 50%, about 6% of the bird species are functionally extinct, and this number is increasing at an alarming rate, right? So there are a lot of these citizen science projects. I'm not sure you have heard about these things. So eBird is, for instance, very popular such project. You might be able to download an app where you are located. And the idea is, volunteers or participants on these projects would basically go about, doing their hiking, and then they would see some bird image, they would record those image, annotate those images, and then this data is then used by scientists for basically tracking endangered species, right? And the volume of this data in general is huge. About 300 million image annotations have been done on these platforms, right? So it's a huge scale. Now, the problem with these platforms is usually that there's a lot of noise in the annotations because the participants, they don't have full knowledge about what species they're talking about. They have some interest and they have basically really excited about doing this, but they might not have the knowledge about what exactly are the species, right? So there has been a lot of research about how to post-process this data, to kind of reduce noise. But the question that we would like to ask ourselves in this machine teaching way of thinking about, if you think about this participant as a learner, can we provide them some kind of a pre-training when they sign up on the app so that their annotation accuracy increases over time, right? So basically, how can we teach these participants to do this multi-class classification, convey those rules in an efficient way? And here again, the optimal teaching data is very important, right? Because you don't want to provide a lot of pre-training phase. You want to somehow give very quick 5 to 10 pre-training phase, and then basically let student participants acquire those knowledge, right? And there are many other benefits of kind of adding the teaching angle aspect to a lot of these applications, because in general, teaching generally increases awareness and engagement of these participants. And another crucial aspect is some of these platforms are actually producing a lot of crucial data sets for training machine learning systems down the pipeline, right? So if we could actually get better data by training participants, you could actually have a lot of other benefits as well down the stream, right? Just to putting together all these applications, right? So basically what we can see is that focusing on the educational setting here, right? A lot of interesting applications where you have intelligent tutoring system and a human learner. And the goal is really, how can we develop smarter tutoring systems which can provide what is the right uh, task that should be assigned to the student, and when student is stuck doing something, how could we provide interventions and what kind of feedback we could provide, right? So these applications are just a small set of applications. For instance, somebody asked here about applications in support sports, and of course, right? So in fact, specifically in educational simulators, a lot of these things that we are doing are in context of games, for instance, right? So you could imagine, so if you're thinking about more like online games, you would imagine something like playing chess, right? So that's a great example where you are normally playing with some kind of AI-based or automated agent, right? And now finding the right opponent, if you have basically a simulator where you could play chess, finding the right opponent which would match the required skills for the human agent would be basically a way of thinking about curriculum here. Also in context of simulators, I think the other kind of games like playing tennis through a simulator and these things would make a lot of sense. One thing to keep in mind here, the focus is on designing algorithms for a teacher. So the teacher here is always a kind of automated machine. We are not talking about human teachers in this context, although we want to get our inspiration for designing algorithms of what a human teacher would do, right? But basically, these are machine teachers. So these are basically machine teachers teaching human learners in these educational applications. Right. So one thing I want to point out here is that when thinking about machine teaching research, so what are the kind of the way to think about a problem, and what are the key components that you should be having in mind, right? And this is how we kind of go about doing research in our group. You start with some application. The application could be, let's say, you are interested in educational simulator. You are interested in teaching classification rules in context of this biodiversity monitoring, right? So that would be the very first thing. Let's start with the application. Let's figure out what is the right knowledge that we want to transfer to the student. Once we have fixed the application and the problem representation, the next immediate question you would need to answer is, what is the learner model that you would like to use as a proxy model, right? Now, these are different questions that you normally wouldn't encounter in thinking about machine learning problems, right? But if you look at, remember that slide from the very first slide, what we had is a teaching algorithm has two things as input. One is the learner model, The other thing is the target knowledge, right? So it's very important that you need have some idea about learner model, because when you would change the learner model, you might end up in some very different teaching algorithm. So once you have fixed a good proxy of a learner model for the task at hand, the primary focus afterwards would be then focus on designing teaching algorithm, right? So for more theoretical projects, for instance, we would cast teaching as some kind of an optimization problem. For more practical algorithms, you might be using some kind of heuristic rules to teach this learner. We will look at some of these ideas later on in this lecture, right? But basically now we have, let's say, designed a teaching algorithm. We have some model simulated learner on which we have done some kind of simulations and testing. Now, one crucial aspect of this research is to actually close the loop and actually test this algorithm in real world on human learners in the educational setting, right? So for that, we would do some kind of user studies to actually get an idea of if now multiple things could go wrong, right? So maybe your learner model was actually very wrong. So even if you designed a very good teaching algorithm for that learner model, that actually didn't make sense for a human learner, right? Or the other thing could be that your model is actually fine, but your algorithm itself was not good enough, right? Teaching algorithm was not good enough. So it's basically a complex loop, but you have to kind of really close this loop and then maybe go back and change your learner model and so on, right? Now, keeping these three components in mind, another important slide, kind of just to give you an overview of this space, is how do we think about different dimensions of this problem space, right? What are different ways to think about research problems or practical systems in which we should design machine teaching algorithms? Now, very first thing to keep in mind is, again, this relates to the first component that we saw in the previous slide, right? What is the type and complexity of the task? And as you would see that as kind of go towards more richer applications, the complexity of the task increases, right? So on the left extreme here is a very simple task. Let's say the goal is simply to teach a binary classification to a learner to classify either it's a 0 or 1, right? To more complex tasks like multi-class classification, teaching language learning where memory becomes important constraint, teaching policies of how to act like in an educational simulator, how to play a game of chess, essentially where you have to take a sequence of actions to be able to perform well in the very end, right? Or to even higher level language constructs like learning mathematics or physics that goes to the right extreme. Another important dimension here is basically what is the type and model of the learning agent, right? Here you could have very simple models, for instance, a machine model, right, which is shown on the left extreme here. On the right extreme are complex cognitive models, right? And then you have space in between, which could be a kind of human-like learning model, which is not too simple and not too complex. And the third important dimension along which we should be thinking about these problems is how much knowledge teacher has about the learner, right? So when we are thinking about theoretical questions, we normally assume a very simple setting, which is on the left side here, where teacher knows everything about the learner. This allows us to quantify more theoretical properties of teaching. And on the right extreme here is basically what you see is more like a black box teaching idea, where you don't really know which learner are you teaching, what exactly are the learning dynamics. And this kind of is closer to real world settings, right, where teacher would also need to learn something about the learner to be able to personalize the schedule, right? So these are three different dimensions. And of course, there are many other dimensions along which one should think about teaching problems. One dimension we have already seen in the beginning, whether a teacher is adversarial or teacher is friendly, right? So that would be another axis here. And you could imagine other axes if you are teaching one student, you are teaching a classroom of students. But these are three dimensions, most important one, in my opinion, that are important for this lecture that we will use, right? So in this lecture, I'm going to split this kind of into three different parts. The very first part is going to look machine teaching from more theoretical point of view. So we're going to spend about 20 minutes on that. So basically, the idea here would be that you have on the left side, everything is kind of simple. You want to teach, let's say, more like binary classification task. You have a very simple learner model and you know everything about the learner, right? So these are information theoretic models that are we going to use for understanding the complexity of teaching. And then there's other extreme, which we have more complex learning settings. The goal is to teach higher level knowledge, and we're going to look at more complex cognitive models which are used in these settings, right? And in between is a space, right, where you can kind of have this interpolation of this space, where you are not dealing with very simple abstract setting or very complex setting, but you can design some learner models and optimize those learner models. So most of my group research is happening in this basically middle box, right? So just to give you an overview of this outline. So part 0 is kind of what we just looked at, right? So just to give you an overview of machine teaching. Part 1, we're going to look at a bit more theoretical perspective of this. What exactly is the kind of the sample complexity of teaching and how does that compare to learning? So that's the left extreme. The part 2 is about the cognitive models of teaching, which is the right extreme. And then part 3, we're going to look at some of the applications in between, depending on how much time we have left, right? So I'm going to move to part 1. I'm going to just quickly look at the questions that are posed here, which are relevant for part 0. Okay, so one question is an example of cognitive models of learning agents. So that's we're going to actually cover in detail in part 2 of this lecture, right? So let's wait for that. And then how does it kind of differ from a GAN? So I think one thing to keep in mind here is that the learner and teacher really are two separate entities, right? So you have, so think about an educational setting. You have basically a human learner who is learning from an app. Let's say Duolingo is a good example, right? Or some language learning app. You have a human learner who is learning, and then you have a machine who is optimizing what is the next thing, next task that should be presented to this human learner. What is important here is that these two are separate entities. They are not aware of each other's internal details, right? So in GANs, you have just one big algorithm where you have two components, discriminator and generator, right? But you have this one big component where they kind of know essentially what they're doing. And those are very much designed for very specific applications. But if you would like to translate those ideas into, let's say, designing optimal algorithms for language learning, it's not clear how to actually design, use those ideas into this, right? So there are some similarities about with GANs and machine teaching. And hopefully some of the theory that we are developing in part 1 of information theoretic models of teaching could allow us to, in future understand better the complexity of GANs. So I think the part 1 of the lecture here is perhaps closest to GANs in terms of perhaps there are some deep theoretical connections that we don't know yet. But if you want to solve some practical problems like in part 2 or part 3, the ideas from GANs are not so easily transferable in this particular setting, right? So hopefully that kind of is not direct answer to basically the question posed here. But what I can say here is at this point, I think there are some deep theoretical connections which we don't know exactly, but part 1 is going in that direction, hopefully allows us to quantify the amount of information that discriminator and generator should communicate to be able to reach some kind of equilibrium, right? So I'm going to go into part 1. So one thing I should note here is that part 1 is a bit more from a theoretical point of view. If you have taken some machine learning course, this should be okay. If you haven't, don't worry about if you're not familiar with some of the concepts. Part 2 is going to look more into cognitive models and from more application point of view, right? So just stay in tune if you feel part 1 bit overwhelming in terms of maths. Okay, so as I mentioned earlier, so part 1 is gonna focus on the information theoretic models of teaching. And the question we really want to answer here is, if you have two entities, one is a student, one is a teacher, and they can only communicate with each other through these labeled data points, how many samples does teacher really need to transfer the knowledge, right? This is basically a fundamental problem in terms of information theory. How much knowledge, how many bits are needed to kind of encode to transfer something from one party to another, right? And what we're going to basically look at here is what exactly is the right way to quantify this sample complexity. How does this sample complexity compares to a learning complexity, right? So this is about 2 decades of work, more from coming from theory community here. So I'm going to start with very simple example, which would hopefully allow you to understand better between teaching and learning. So still related to the very first question on Slido, how does teaching and learning differs from each other? So let's see this difference on a very simple setting, right? So let's say the goal is simply to teach an agent, which could be a machine learning algorithm, let's say, to classify images between two species, between Wavell and Vespula, right? It's a very, very simple setting. There is only one feature associated with these images, right? And that feature is about, let's say, the color contrast level, right? So there is one feature denoted as X. So the images could have low color contrast on the left extreme here, and they could have high color contrast on the right extreme here. And basically, we have a set of hypotheses or the decision rules. And in this case, we're going to look at something very simple, which is we have some kind of a threshold functions. So threshold is, for instance, this green line is the correct threshold here. So everything, there is a threshold. Everything to the left of that is going to be Wavell. Everything to the right of that is going to be Vespula. Okay. And I'm also trying to introduce some notation along the way, by the way. So think basically what you have seen here is there is a calligraphic X, which represents a set of images. In this case, in more cognitive settings, more complex learning settings, X could represent a set of exercises or algebra problems, right? Then you have set of hypotheses, which depends on the learner model, but this is basically the set of rules, and one rule out of those is the right representation. And then there is H star, which is basically the right knowledge that we want to transfer. Okay, so that's basically the view. And now let's see how one goes about solving this problem from a learning point of view. Okay, so the very simple learning setting is what is called passive learning, right? So in passive learning, the idea is that a learner knows about calligraphic X, calligraphic H, but doesn't know about H star. And learner is receiving labeled data points from some environment or from some oracle, right? So in learning, we not care about that oracle itself, but we are basically receiving data points. So we are designing this learning agent algorithm, right? And the goal here is how many samples this agent would need to be able to exactly identify H star. Okay, so it's receiving more and more of these data points. Now, just try to think this in your mind. Is these data points enough for you to exactly identify H star, right? Normally, we would have done this through some kind of a poll, but before I give you the answer, just think, right? So it's receiving more and more data points. Now, at this point, it has received 4 Vespula examples and 1 Wavell, 4 Wavell examples and 1 Vespula example in pink, right? However, at this point, learner cannot exactly identify H star. Okay. Now, at this point, learner can exactly identify H star because it has received essentially 1 point to the left and 1 point to the right. There is no other H star possible after this here onwards, right? So this is the way to think about when you're designing, let's say, a learning algorithm, you're receiving labeled data point and you want to infer where the target decision boundary is. Okay. So in this case, passive learning is kind of data coming IID from some distribution. And here you would roughly need, order n examples. If your data set is of order n, what can be shown is that you would roughly need a large number of examples to be able to infer this decision boundary, right? Again, I'm using a very simple, the most simple model problem setting here to just convey the high level ideas, right? A bit more powerful setting is what is called active learning. I'm not sure if you have heard about active learning, but the idea is that in active learning, learner can actually ask questions itself smartly, okay? So now if you are actually designing active learning algorithm, now you might be wondering, what would be the very first question you might want to ask? Okay. So as it turns out, the best question to ask here is somewhere in the middle, right? Because you know that if this turns out to be Webble. Everything to the left of it is also Webble because of the linear threshold structure in the problem. Okay, and then you go into the right side of this leftover points. You ask the middle point there. That's Vespula, and then you keep on doing this search until you have figured out this decision boundary. Okay, um, so what one can see here is that if you give the learner the power to select these examples more carefully, it can really figure out the decision boundary exponentially faster than passive learning settings, right? So it's a log n versus n. So that's basically two learning paradigms. Now let's look at this problem from a teaching point of view, right? Now teaching setting is somewhat different. So teacher as input gets already this H star, right? Teacher already knows that the decision boundaries here. So teacher has more knowledge than the learner. And it also has a learner model. It knows that learner is behaving as if in the passive learning setting. So when whatever data teacher provides to the learner is going to basically be inferring H star from top of that. Now you might be wondering how many data points this teacher would need to convey this green boundary to the learner, right? So you might want to guess in your mind for 5 seconds before I give you the answer. Okay, so the answer here is basically very simple. Teacher would only need 2 data points to convey this decision boundary to the learner, right? Um, because it knows that learner is essentially trying to infer H star and it's looking at all possible decision boundaries. And after you convey these two examples, there is no other H star which is possible. Okay, this is kind of because of the structure of the problem, right? So the problem has linear structure. They have agreed upon on the hypothesis class. So teacher and learner both know that hypothesis class is this threshold functions, and only 2 data points are needed, right? So the main point of this slide is really that the way of thinking about designing learning algorithms could be very different from the way of thinking about designing teaching algorithms, right? Uh, and the sample complexity could be drastically different. So in the learning setting, you have different powers to the learner, passive learner, active learner, and in the teaching setting, teacher already has a lot more information than the learner, and it's more about how could one convey this information back to the learner, right? Again, keep this in mind. This is very simple setting, right? So we are considering a teacher who knows everything about the learner, and then teacher exactly knows how learner is going to process this information. But for more interesting things, kind of more interesting research questions, we are kind of always dealing with more complex settings, right? Now, this is the point where I think it's good to think about the connection with GANs. So some of the problems that we have been thinking about in the third part, for instance, in the teaching setting, what if learner and teacher don't know about each other, but they want to somehow collaborate, right? So teacher wants to convey certain information to the learner. Teacher doesn't exactly know everything about the learner. Learner doesn't know exactly everything about the teacher. How should they convey information? What kind of questions learner should ask? What kind of information teacher should pass it to the learner so that this information exchange can happen as quickly as possible? I think those are some very interesting questions. So we have, so later on I'll point you to some of the recent publications. So what we have looked at is, if teacher and learner are collaborating together, the complexity of teaching could be even lower than this number 2 here, right? So number 2 is actually you could actually just teach with even one example in this case if teacher and learner are collaborating with each other. So, but I can tell you a bit more over later on the Slack channel. How can you get teaching complexity of 1 for this example under this some stronger notion of collaboration? Okay. So now just to formalize this setup a bit more, right? So what we have seen here is, to kind of represent this problem, we have set of unlabeled examples, which could be Wavell and Vespula images here. You have some hypothesis class, which are set of functions, in this case, are binary functions, and you have some target hypothesis there that we want to teach, right? One way to represent problems, especially for theoretical studies, are through this kind of a matrix representation. You have basically a set of hypotheses as rows, you have set of labeled examples as columns, and then you have one of them as H star, right? So this could be one way to represent problems in this abstract format. Now, I will also set up the teaching interaction. So this teaching interaction you would see also is important for part 2 and part 3 of the lecture, right? The way teacher and learner going to interact is, learner going to start with some initial knowledge H0. At time t, teacher would pose some quiz to the learner to infer its current knowledge of ht minus 1, and then teacher would select next example, and learner would update its knowledge based on that. And teacher would stop when ht equal to h star, right? So this is kind of the basic interaction, and depending on the application, you can change this model of interaction. For instance, what does it mean for teacher to estimate learner's current knowledge, right? In more complex application, this could mean teacher giving the quiz to the learner. In this particular application, with theoretical point of view, we could also assume that teacher knows everything about the learner, right? So this is kind of a high level notion of interaction. And now that kind of, if you go back to that diagram with 3 different components, so what we have set up so far is what is a way to represent our application and the problem. And now next important thing is what is a way to reason about a learner model before we can design the teaching algorithm, right? Now, I'm going to introduce a learner model, which is used for this more theoretical abstract studies. This is kind of the very simple learner model, which has been used in last 2 decades, right? And the learner model is something very simple. So the name might sound complicated, but it's actually very simple. And the idea is that learner would maintain some kind of eligible rules or hypotheses, which are still consistent with the data it has seen, right? So at t equal to 0, it starts with the capital H0 as the set of eligible hypotheses. And whenever it receives some new data points from the teacher, it would update its eligible hypothesis, right? So this is basically the kind of learner model. In fact, this is the model that passive learner that we looked at before was using, right? So it receives more data points and then it eliminates hypotheses which don't agree with those data points, right? So with this learner model, the formal model of this learner in this setting is really learner starts with some initial H0, small H0, and small version space, initial version space denoted as capital H0. At time t, learner would receive a labeled example from the teacher. It would update its version space, and then learner would select a new hypothesis from that version space, right? So this is basically kind of the model that we are using here, right? Now what we have said so far is the problem of teaching binary classification, right? So that's in this application. We have set up a learner model, which is a version space learner model for this theoretical study. And then we're going to look at how does one go about designing a teaching algorithm, right? In this theoretical setting, it's more about we're going to look at more from an optimization point of view. What is the corresponding optimization problem that teacher should solve to come up with the smallest teaching set for this learner, right? So the problem from teacher's point of view is as simple as you can imagine, right? So basically what teacher is looking at is really find the smallest sequence of labeled data points that it would provide to the learner, so that when learner receives those data points, it would output a hypothesis H star, right? So that's kind of the simplest possible thing you could imagine, right? So it's basically just want to steer the learner to reach this target H star and how many examples it needs along the way to get there, right? One of the classic result here is that to actually find this optimal sequence is an NP-hard problem. I'm not going to go into details, but you can always ping me later on Slack and we can discuss some of these details. Right, so this is an NP-hard problem, but what also is known that you can actually pretty much approximate this to some close factor, right? So there exist some approximation algorithms to be able to find this optimal sequences, right? One thing to note here is that even for this very simple problem of teaching binary classification, even under the setting where we know everything about the learner, the problem of finding optimal teaching is a hard problem, right? And as you make the problem more and more relaxed, more practical, the problem only gets harder, right? So if you basically don't have essentially a full knowledge about the learner, then you would need more complexity, right? So there have been a lot of kind of interesting research questions in this flavor. So one thing I would like to mention in this theoretical studies is that how do we quantify the complexity of teaching? And here, one important complexity measure that is basically introduced about 2 decades ago is what is called teaching dimension of a problem, right? And here, let me go to the definition quickly. But basically, the idea is the following: we want to quantify, given that metrics, right? So given set of examples and hypothesis class, how complex that matrix is to teach. Right? So that's the key theoretical question in this information theoretic models of teaching, right? And the way to quantify this complexity is the following. So as you can see in the bullet points below, first, let's talk about what is the complexity of teaching one H star in that class, right? So TS is the teaching sequence for H star, and what you see in this as a size of the optimal teaching sequence for teaching H star. Okay, and then the complexity of teaching this whole class is basically taking a max over any H star. So if any of the hypotheses could be a target hypothesis, that would represent the complexity of teaching this class. Okay, so this is one of the fundamental measures of teaching dimension of a problem, right? And there have been a lot of new variants of teaching dimension in last 2 decades. Some of our recent work that you would see in our publications is also has introduced some more interesting variants of teaching dimension, especially where learner and teacher are collaborating under some interesting scenarios. Okay, so just to give you an example of teaching dimension here. So let's try to just walk through this simple example. So let's say this is the problem. So you have 5 examples, you have 5 hypotheses. Let's try to first compute what is the optimal teaching sequence for teaching H1. Okay, so I would like to just walk through this example. Just think about 5 seconds, and then we basically see that this is actually very easy to answer here. So how many examples a teacher need to teach H1 to the learner, right? So the answer here is actually it only needs one example. For instance, it could pick X1 with a label of 1, right? So if you pick X1 with a label of 1, it's clear that H2, H3, H4, H5 can't be the target hypothesis. So X1 with a label of 1 is enough to teach H1 in this case, right? So, and you can similarly argue about, for instance, how many examples are needed to teach H3. You would need 2 examples. For instance, if you say X2 is 0, X3 is 1, those 2 examples would eliminate all other hypotheses, and that's enough to convey this number. Okay, so in this case, then the teaching dimension of this particular matrix is basically the max of the numbers that you see in this column, which is 2. Okay, I'll have one more example here. I will not try to go this in detail, but you will see this in your video stream, right? Later on, you can, when you're going over this video again, you can see how did we come up with these numbers 11114. So in this case, then the teaching dimension would be taking a max of that column, and the teaching dimension of this problem is 4. Okay, and one fundamental question of one of the reasons about studying these information theoretic models here is that really to understand how does teaching compares to learning, right? How many samples a teacher would need when it knows everything, how many samples a learner would need on its own, how many samples they would need when they're collaborating, for instance, right? One question is really that was posed about 2 decades ago is, for instance, how does teaching dimension compared with VCD of a problem? So if you haven't heard about VCD, that's basically one of the complexity measures which is used in the learning theory to quantify the complexity of learning a problem, right? And this has basically been one of the key questions that was long time open, but what we know now is that the complexity measure TD that was introduced about 2 decades ago is not a very right measure of measuring the complexity, because it kind of assumes no collaboration between learner and teacher, right? So what it ends up happening is that there are problems which are very easy for learning. So this is a matrix. I will not go into details how VCD should be computed for this matrix, but this is a problem where VCD of this problem is 1. So it's a very easy to learn. is basically just a kind of a diagonal matrix with a row of zeros. So it's very easy to learn this matrix from a learning point of view, but it turns out that it's actually very difficult to teach this matrix. Again, I can tell you how to compute teaching dimension and VC dimension later on a Slack channel. But basically, so what it turns out is that this classic notion of teaching dimension doesn't have a good connection with VC dimension. And this had led to a lot of research, specifically in last 2 decades, where new notions of teaching dimension have been discovered. One interesting notion is what is called recursive teaching dimension, which goes into some kind of a collaboration between teacher and learner, right? So if there are two entities who are kind of thinking about each other, but only communicating through labels, how many samples would be needed, right? And that number turns out to be much lower than TD. And I think that's kind of goes back into the GAN's question. I think that's kind of the theoretical underpinnings somehow are common, right? How many samples are needed to convey a knowledge when two entities are collaborating with each other? I think that's kind of a very interesting question, fundamental to computer science in general, right? So recursive TD is one new notion that has come up, and we have been doing some recent research as well on this to come up with some interesting, more modern notions of teaching dimension. But basically, let me conclude this part with saying that this perspective, the information theoretic models of teaching, has primarily been useful to understand how teaching complexity compares to learning complexity. There has been a lot of interesting work from colleagues Sandra Ziles, and there has been very interesting work of what is the teaching complexity for more complex models, right? What would be the way of measuring complexity for teaching an SVM? So there has been a lot of interesting work from my colleague. I've added the link here from Zarizu. The basic idea here is that these things are perhaps useful for teaching. For instance, they are useful for understanding the theory of teaching. They are useful for training set poisoning attacks, when you are actually trying to attack, let's say, an SVM model, but perhaps they are not so effective when you want to actually teach people, right? And I want to finish this part with this particular slide. If you go back to this problem of teaching Wavell and Vespula to people, so let's say we use a teaching set produced by this very simplistic model. It would say that let's use these two examples. Let's use this Wavell and Vespula teaching set of size 2. And the question really is that, is this a good teaching set when we are teaching human learners, right? And these are the two examples that this particular algorithm would pick, right? And perhaps you might want to think, right, what goes wrong when we would use this particular teaching set to teach people? Well, as you can probably see, is that there is not a lot of information content or interpretability built into these two data points, right? In fact, that was the way this algorithm operated, right? So it picked two data points just next to the decision boundary. And those are actually the data points which might be very confusing for human learners, right? And the problem is that as a human learner, people would have limited inference power, and there is a noise in this processing. They might not be able to make any sense of Wavell and Vespula when it's given just side by side like this, right? Very close data points. So for instance, you might want to give data points which are a bit farther away so that one could convey a bit more clear message of what we are trying to teach. And of course, there are a lot of other things that one has to keep in mind when teaching people, right? For instance, in language learning platforms, the memory of human learners would become very important. The engagement of human learners would become very important. You need some kind of interpretability built into it so that they can make a sense of this. And this is especially important when the representation, the feature representation that machine teacher is using is different from how human learners are looking at these data points, right? When looking at more complex tasks like in this educational simulator, you have to add more constraints like safety, right? You don't want to give a task which student has no idea how to do, and they might end up doing something very bad, right? And for instance, questions about fairness, right? So if you're teaching a classroom, how do you teach to make sure that everybody gets some important information? So you don't want to basically focus only on a particular segment in the class, right? So there are some interesting questions of fairness that would come in there. So That basically concludes the part one of the slide. Now, the main message is that information theoretic models are very useful for dataset poisoning attacks. They are very useful for kind of understanding the theory of machine teaching, but perhaps they are less useful when we want to actually teach people in educational settings, right? And that would bring me to part two of this lecture. But before we go there, let me have a quick look at questions. Okay, so there's an interesting question on slide 16. If one data point is enough to teach, so let's have a quick look. Okay, good. So now after being given good info, yes, I think thanks for asking this question. I think it's a great point. This is essentially what I was referring to, whether learner and teacher are collaborating or learner is just basically very passive and is kind of even not trying to learn unless it's kind of forced to learn, right? So the class, so what I presented here is really kind of more like a pessimistic teaching scenario where learner, we don't assume anything about the learner. And we can be sure that after we have given those two teaching data points, learner would exactly output H star because that's the only valid hypothesis left after that, right? And this is kind of the notion of classical teaching dimension. So, and that's why it's a little pessimistic, whereas a more interesting notion of teaching dimension, in fact, that's what recursive teaching dimension is, what the participant has written here, that after given one data point, after you have given, let's say this Wavell, that this data point is Wavell, now learner could actually automatically infer that if teacher has given me this data point as Wavell, it must be that the green boundary is here, right? So if they're actually collaborating in a game theoretic sense, you only need one data point, and the recursive teaching dimension for this problem is actually one, whereas the classic teaching dimension for this problem is actually two, right? And they have been even more interesting collaborative notions of teaching and learning that in fact we have been studying in our group as well. But that's a great question. Yes, so I think the question about how do we approach open question systems, I think perhaps part two of the lecture slide would make it a bit more clear. I think part one is really not about too much about open question answering system, but part two, I think, allows you to kind of incorporate some of these richer signals from the student back into this. Okay, good. So I hope that clarifies this question. But you are exactly right. We need one data point if we learner and teacher are collaborating here. Okay, so that brings me to this part, right? So what we have looked at is the left viewpoint of this model. Now we're going to go to the right extreme and look at the cognitive models of teaching. And so these are actually the models which have been extremely popular in real world applications. So two important platforms that actually use models of this style are, one is assessment platform that I showed you in the beginning, where students can solve algebra problems, for instance, and then the platform would actually decide what are the problems that should be given to the students. And the other platform is Carnegie Learning. These platforms actually have some of the data sets available online, and that has led to a lot of interesting research in last 2 decades. So somebody who's looking into more practical development of these things, I think assessment data set is one of the data sets which is available that one could go about trying some new algorithms, right? Now in these cognitive models, the way of thinking is very different, right? So now we are really going into teaching more complex concepts, right? So there is no hypothesis space as such, but basically what we have is really some notion of a skill, right? The idea is that each task is associated with certain kind of skills, right? To solve that algebra problem, perhaps you need a skill to apply congruence theorem, and you need to solve some multivariable equation, right? The idea is if you have those skills, you would be able to solve the task correctly. Otherwise, you wouldn't solve it, right? So very basic idea. And the second idea is that as you practice a skill more and more, you would be basically able to acquire that skill. Right? So that's the very basic idea of what is called knowledge components or knowledge tracing, right? And let's look at this through an example. So this is a problem where somebody, basically a participant or student, has to find the value of df, and it requires two things to solve this problem. First, you need to be able to solve the value of x on the left triangle, and then you need to apply congruence theorem to see that df equal to ac, right? And one way to think about problems in this setting is that you have two skills in this: how to apply congruence theorems, and then how to solve one variable equations. And let's say you have a bunch of exercises, right? And you could have some exercises x1, x2, x3, which only require skill C. You have exercises 4, 5, 6, which only require skill V. And then you have exercises 7 and 8, which requires both the skills, right? So one way to think about this application domain is through some kind of a bipartite graph like this. So for the purpose of this lecture, let's consider even simpler setting, right? So in real world, the setting is very different. You actually have 125 skills in assessments, and those skills are interconnected with each other with prerequisites. It's not really a bipartite graph, but a complex graph. So let's consider a very simple setting, where there is no prerequisites. Every skill is on its own, and each task only requires one skill, right? So there's really one-on-one mapping going on here, just for simplicity of the presentation. So in this case, again, what we're going to do is really keep that three components in mind. We're going to start with understanding the problem representation and teaching interaction under these cognitive models. I'm using the term BKT, which basically stands for Bayesian knowledge tracing models that we're going to study here. Once we have set up this problem representation and interaction, then we're going to go to formalizing this BKT model, right? So the basic idea is as follows. So you have different, do you have a knowledge component? Let's denote it as K. So you could have multiple knowledge components. For each knowledge component, we would denote learner's state as HK to be 0 or 1, right? So basically, for a knowledge component K, learner could be in state 0, which means learner doesn't have a mastery of that skill, or learner could be in a state 1, which means learner has a mastery of that skill. Okay. And the interaction between teacher and learner is going to go as follows. This interaction actually exactly looks as the way interaction was in part 1, right? What's going to happen is at time t, teacher is going to pick xt. Now xt has a different meaning here, right? So here is really an exercise, whereas in the previous part, xt was one labeled example, right? So teacher picks an exercise, let's say associated with knowledge component k, and learner would attempt that exercise using its knowledge at time t minus 1. So I'm still, for simplicity, just assuming learner provides a 0 or 1 answer, right? But this goes back to this question about that you could actually get a lot more complex signals from the learner, okay? So instead of 0, 1, you could actually see the learner's full attempt, which would allow you to actually infer something more about the learner. And at the end of this teaching time step, learner would update its knowledge from HKT minus 1 to HKT, right? So that's basically learner's update about the knowledge. And so that's about the interaction. Now I'm going to basically formalize the Bayesian knowledge tracing learner model, right? So this is one of the most popular cognitive model that is used in these real world applications of intelligent tutoring system assessments that we saw earlier. So the learner is modeled with a few key parameters. This is, in fact, one of the classic version of BKT model. There have been more advanced notions of BKT model that have come up in last 2 decades, right? The very first thing to model is what is learner's initial knowledge about a particular component, right? And so here this is captured by the parameter pkinit. This basically means what is the probability that when learner comes here, they already know this particular knowledge, right? And then the second thing is about learner's response. This basically means that what is the conditional probability that learner would answer a question correctly when they don't have that knowledge? conditional probability of slipping, which means what is the conditional probability that learner would not be able to answer a question when they have that knowledge, right? And then the final important parameter is what is the conditional probability that they would jump from state 0 to 1. Okay, so that's basically a very simple view of thinking about this particular model, right? And now let me give you a bit more modern view of reasoning about this model, more like a temporal process, right? How do you actually uh, kind of think about this model over time? And here what you see on top is kind of the hidden state of the learner, which is shown in these grayed out boxes, right? Learner state at t minus 2, t minus 1, t. And what you see below is basically learner's responses coming out from those. These are the observations that we actually get to see. So there is this term called dynamic Bayesian network. Some of you might have seen that in AI or ML course, but basically this is a way to represent BKT model, right? So it's still that model with 4 parameters, but we're going to represent it through this framework of what is called dynamic Bayesian network. Now, those 4 parameters I'm going to map to this network. Okay, so the very first thing is, if you go back to the start of this network, what is the probability that this one of the gray box start with the state of 1, right? That's the probability pk in it. Now, next, what we need to put are the numbers, so what is the probability that you would see by t to be 1 conditioned on its knowledge at time t minus 1, right? And these are the numbers that we saw earlier. Yt equal to 1, given that learner doesn't have the knowledge, is pk guess. Yt equal to 1, given that learner actually has a knowledge, is 1 minus pk slip, right? So these are basically the parameters that we introduced, right? So so this is 1 minus pk slip, right? Because what we introduced was yt equal to 0, given hkt minus 1 equal to 1. Okay, so that's basically about conditional probability of responses. And the third is how does learner change its knowledge? Those are the parameters that basically defines this particular edge on the top, right? This is basically saying what is the conditional probability that hkt at the end of time step t, learner is in state 1, given that learner was in state 0 at time t minus 1, that would be pk learn. And basically what is the probability that learner stays in state 1, that's 1. So in this case there is no forgetting, right? In the classic model there was basically no forgetting built into it. Now so that's about the learner model, right? So basically what we have seen so far is that we have set up some problem representation through that graph, bipartite graph that we saw. We have set up the learner model, and now comes how do we think about teacher, right? What would teacher do in this case? In part 1, teacher was really solving that optimization problem that we looked at. And in this case, teacher is more interested in doing some kind of a prediction and inference about learner, right? So what does prediction mean? Can we predict what is learner's state, what is learner's response gonna be in future? Inference means, can we actually infer what is the knowledge state of the learner, right? Has learner really mastered that skill or not? That's what we would like to understand. So just to set up some notation here. So we have, let's say we have learners responses at the end of time t, denoted by this dt. So this is basically everything that we have seen from the learner. Right, again, I'm going to use these binary responses, but these y's could be really more complex. And what we are really interested in is predicting learners' future responses, right, based on how they have been performing in the past, and to infer learners' knowledge at the end of time step t. Okay, and I think the details are not important. What is really the takeaway message on these few slides here is that these computations can be actually done very efficiently. So the dynamic Bayesian network allows you to basically compute this efficiency by applying simple probabilistic rules, right? What I would show in next slide is, what is important to note here, by the way, is that you knew theta k0, learner's initial knowledge at time 0, that was essentially pk in it. And what I will show you in the next slide is that if you have estimate of learner's knowledge theta k t minus 1 at the end of time step t minus 1, you can easily compute learner's response in future. And you can update your belief about learner. You can update theta kt from theta kt minus 1 and yt. Okay, so I'm going to just show you this direct formula without actually going into, I have some slides with the derivation, but I would leave it here on the slide so you can actually follow these steps later on. Well, what is really message here is that, first of all, you can very efficiently compute learner's response, or how learner is gonna perform particular exercises in future. And the formula is actually quite intuitive if you would actually spend time thinking about this, right? So it's really based on the basic parameters that we looked at earlier. So it's based on pk sleep, pk guess, and it's based on our belief about learner's current state, which is theta t, right? I will not go into the derivation, but it's based on very, very simple probabilistic rules. And you can see that in 6 lines, you can actually get this basic formula of prediction about learners' responses. And you can also do prediction more far into the future, right, by just kind of integrating out some intermediate time steps. Now, the other important thing is, how can we predict about learners' knowledge? How can we infer or update our belief about learners' knowledge at time step t based on our belief about learners' knowledge from time step t minus 1? And this again can be done very efficiently using these few lines of computation here. I'm going to leave the details on this slide, but basically I will not try to prove where does this come from, right? So let me show you in how one would actually use this in practice. So let's just consider a very simple example, right? So let's say we have a setup where we are using these 5 parameters. I'm going to show you an example of prediction and inference, basically. Right. So we have basically this pk init to be 0.5, pk learn to be 0.2, pk guess 0.1, pk sleep 0.1. And let's say we start interacting with students on this intelligent tutoring system, right? So this is kind of the view of intelligent tutoring system, who is trying to predict how students going to do in future and what exactly is their mastery of the skill, right? So what is kind of important to note here is that, in the beginning, you start with some belief about 0.5, 0.5, and then you look at, you predict what would be the learner's probability of, this is basically your prediction that learner would output 1 or 0. And you actually then see learners actually attempting the exercise. You see that student 1 got it correct, student 2 got it wrong. Based on this, you would actually now update your belief about the learner. So for student 1, your belief that they have mastery the skill is 0.92. For student 2, it has gone down to 0.28. Now you would again do a prediction. What is the probability that learner would do this exercise correctly? That is 0.84, 0.32, based on the formulas that we saw earlier. You can actually later on verify that. You can easily get these numbers based on the formulas we saw in the last few slides, right? And then you again observe students' responses to be 0 and 0. And then basically we keep on doing this inference and prediction over time, right? So that brings me to this particular slide, just to put all these 3 different components together, right? And this is basically the same 3 different components that we saw earlier, and how we would apply these to these cognitive models, right? You would start from some application, for instance, this assessment platforms or hour of coding platform, right? And generally, we have a lot of data sets available from these platforms, which would allow you to fit the parameters of this BKT model, right? So this BKT model, for instance, has these 4 parameters, but it could be more complex with more complex problem settings. You would do some kind of parameter fitting to actually fit these model numbers, right? And then you would run your teaching algorithm to be able to infer basically how learner student is going to do in future, right? So they are basically, yeah, so I think the point that I mentioned earlier, right? So there are publicly available data sets that allow you to do this fitting, to design a teaching algorithm, and then do some kind of cross validation if your teaching algorithm is performing better or worse, right? So there have been 2 research themes that I want you to point out here, right? So one research theme in this cognitive models is really how to design better learner models, right? One thing, for instance, you notice that there was no forgetting built into this BKT model, right? Um, and how could you update that dynamic model to add this forgetting? How could you add some kind of personalization components? How could you know, incorporate another node into that dynamic network which captures individual features of the student? And how can you automatically learn that graph from the data, right? So that's about improving learner model. The other big research direction here is how can we use these models to actually come up with designing teaching policies, right? And they have been basically two different parallel threads here, right? One is how can we use our belief about learners' mastery to decide when to stop, and how can you actually come up with the plan of the whole curriculum in that dynamic network. Okay, so I'm gonna show you this particular slide. Basically, just to give you an idea, how could one update this model, classic model, to incorporate forgetting? Right? So just try to think where exactly the forgetting, what do we need to change in this model to add forgetting? So the first one is about learner's initial knowledge. So that has nothing to do with forgetting, right? So this number is fine. The second one is how learner is responding based on their current knowledge. So this has nothing to do with forgetting. The forgetting part is really about here, right? So what is the probability that learner would have mastery of the skill at time step t, given that they had mastery at time t minus 1? Right now, this number is 1, right? And if you want to add forgetting, we need to add one more parameter here. Okay, so I'm gonna basically jump a bit ahead into this, but what I want to convey here is that there's basically 2 decades of research enriching these Bayesian knowledge tracing models, and I can point you to some interesting references later on if you want to understand a bit more complex variants of Bayesian knowledge tracing models here. Okay, so one thing I want to jump to here is basically this slide. Now, given this model, how can we design teaching curriculums, right? Because in the end, that's kind of important ingredient to be able to optimize the curriculum for the students. And there are some recent works on this, but not so much, right? So this is basically one key limitation, in fact, of these cognitive models, that the models are too generic and abstract, that they are good for prediction about learners' future responses, but they don't allow you to really design an optimal curriculum on top of it, right? Something like an optimization problem that we saw in part 1, this is very difficult to cast for these particular models. Okay, so one popular way of using BKT for teaching is, you have your belief about learner skill, and you would keep teaching a particular skill until you know that they have mastered the skill with more than 0.5 confidence, right? There have been some recent work on really how to design the whole curriculum end to end by using some kind of reinforcement learning techniques on this dynamic Bayesian network. And there has been also some recent work on designing more robust policies, because learners going to have a lot of fluctuation going and up and down. How can we really say that this is the time to really stop, right? One important takeaway message from these models has been that sometimes better predictive models do not lead to better instructional policies, right? Because the thing is, these models are too complex, maybe difficult to optimize in terms of teaching, and if you make the model more complex by adding even more parameters, that might make the prediction better, but that might not help in the actual teaching goal for these models. Okay, so just to summarize this cognitive models, basically the Bayesian knowledge tracing model that we looked at here, these are very well studied cognitive models actually used in real world applications. These are generic models. You could actually model any complex task like learning algebra or learning some higher order mathematical skills. And the key limitation here is that these are models good for prediction about how learner is going to do in near future, but they're not so good in designing the end-to-end curriculum about learner. And they do not give you fine-grained details about, when learner is actually solving a task, how exactly they're going to do it, right? So you cannot get a sense of 0 or 1, but you don't have very fine-grained models. You need to enrich these models with more details so you can actually provide some real-time feedback to the students. So So you don't have a kind of a computational aspect of things, how somebody's going about doing solving this exercise, which is very important when you actually want to do some interventions. So that brings me back to this overview slide, right? So what we have looked at so far is these two extremes. The left extreme is about understanding the theory of machine teaching, which goes back to the very fundamental information theory questions given two entities who are communicating with each other through some labels. How many samples are really needed to convey information, right? And we saw that depending on how much collaboration there is between these two models, and what does one entity assume about another, there could be different answers to this, right? This is a fundamental question in computer science in general, right? Which basically is something that has been studied in more information theoretic sense in machine teaching literature as well. On the right extreme, we have seen more application-oriented cognitive models, more specifically Bayesian knowledge tracing models, which are actually useful in real-world applications to predict near future, near-term performance of the student, but they might not allow you to do a long-term planning. So we are not there yet. And these are both very active areas of research. On left extreme, we have been kind of thinking about more interesting notions of collaboration between learner and teacher. On the right side, we are thinking about how can we take these knowledge tracing models and use them to actually design curriculums or add some more richer signals into it so we can do some interventions, right? And in between is basically this space. And how this space differs is that we don't want a very abstract model like for teaching Boolean functions. We don't want a very complex cognitive model. We want something in between, right? So we want something which is kind of a suitable for the application at hand, so that we could somehow get the best of both worlds. We could really analyze a model. So we could use some human inspired computational model, which is just good enough for the application at hand. And we could do really optimization over this model to come up with the good teaching curriculum, right? So that's where most of my research is focused on. So we work also on the left extreme, on the right extreme, and a lot of our current work is kind of focused on this particular box. So before I go into this, I will probably not go into the details, just to give you a high level overview. But let me go back to Slido and see what are questions related to part 2 and perhaps also for part 0 or 1. And then depending on how much time we have left, we will go into this part 3 here. Okay. So I guess most of the questions are answered here. There is a question about data sets. I think I would request the participant to pose the question perhaps slightly differently. It's not clear to me what exactly is the intent that they have in mind. So the question is, I heard the requirement is way less than ML. So what if the prior wrong noisy points? So it's not clear to me exactly the intent that they have here, but I'll be very happy to answer this question again when they pose it. And I think the connection with GAN is hopefully a little bit more clear with especially the recursive teaching dimension idea that I mentioned, right? So where learner and teacher are collaborating with each other, and the question of how many samples are needed to really convey information from one to another. I think that's kind of has some very deep, interesting theoretical questions for GANs, but we don't have that deep understanding of GANs in terms of sample complexity as we would like. And the difference between machine learning and teaching, I guess that's perhaps we have discussed quite in detail, right? In terms of formalism as well as in terms of applications. So I would just check with the organizers here. So Maria, so roughly, do we have to stop at 2, or should we use the rest of the time as well for lecture content? Okay, so I'll just continue with the content here, because I guess the plan was first 90 minutes for lecture and last 30 minutes for Q&A. But since we are doing Q&A along the way, I think I will just continue until organizers ask me to pause here. So next, I'm going to give you a very quick overview of some of the applications, some of the research that we have been doing in our work, right? So one thing, I'm going to just give you some quick overviews, and I'll go into one of the application in a bit more detail. So some of our recent the work that we started with machine teaching has been inspired from this teaching multi-class classification rules to people. In fact, this was some of the earlier work that I started during my PhD times, and there we kind of did really cool experiments with this Babel and Vespula, right? So the slide that I showed you, what is the problem of teaching using this information theoretic models, right? You get these two examples of Babel and Vespula, which might be too complex for human learners. So we developed really more human-like classification models, and what we showed was that if you actually now optimize teaching data for those models, you can actually really get performance guarantees, as well as they actually tend to work really well on actual human learners through extensive user studies, right? So these are references that actually I just pointed out here. I'll have a link to our publication page, which you could actually go and dig a bit more into details. So one application that I'm gonna focus on, unless more questions come up, one application that I'm gonna focus on in for next perhaps 20 minutes is going back into this language learning app, right? So, and here we looked at, basically how can we optimize curriculum of those flashcards for this language apps, right? So this is a recent work from 2019. Again, to get into more details, I would really recommend to reading, going through the paper, but I will give you some quick high-level overview of what we actually did, right? And as we looked at earlier, this is a basically slide from introduction. That the question really is that we have these apps which are very popular, but what can we say about um, the schedules that are produced in these apps, right? Or what exactly is a way to quantify this is a better schedule than that, apart from doing user studies? But before we even do user studies, can we give some formal guarantees that this schedule is going to do better than that, right? So that's basically what we studied. So before doing that, let me try to formalize this problem. And again, for posing the research question, it's always good to abstract out the problem a bit, come up with a clean problem that we could actually kind of have a good handle on. And the clean problem that I'm going to pose here is basically is going to remove some of the details, but the simple problem is as follows. Let's say we have n concepts that we want to teach, right? These n concepts could be, for instance, flashcards, right? 10, for instance, one application is language learning for German language, right? So these are n different flashcards, each associated with an image and a corresponding English and German word. And let's say we have capital T total learning steps. These are the steps when app and student are going to interact, right? And this interaction between student and the app, you could model it something like this, right? So basically you have basically at each time step, app is going to display a card to the student. For instance, you see on the right side number 1, then student is going to attempt that card. Again, I'm going to use for simplicity 0 and 1 response, but here you could really enrich the response to be, for instance, how close the student's answer was to actual answer, right? And then teacher would actually provide an answer to that student, which is number 3 here, okay? And over time, you could imagine this kind of interaction between student and between app and student, right? Time step 1, 2, 3, 4, and so on, right? And the idea is that we would like to pick a schedule of these cards based on what we have picked in the past and based on learners' responses, right? And what is the optimal schedule of displaying these cards? That's basically the question we are asking here. Okay. Now, just to get an intuition about how one should go about doing this, I think it's good to think about what would be some naive way of designing these teaching policies, right? So let's consider a very, very simple example. Let's say you have 5 concepts denoted as A, B, C, D, E. And let's say you have this 20 different time steps in which app is going to interact with the student. Now, one very trivial baseline technique you can think of is just a random policy, which just picks an example randomly, right? So, for instance, this is one of the random schedule that I have displayed here. Another naive baseline could be a round robin policy, which would just go over the concepts A, B, C, D, E, A, B, C, D, E, right, and so on. Now, what you think is the limitation of using these policies? Uh, well, one limitation is that they are totally agnostic to learning process, right? They basically have totally ignored if student is learning or not, which concept they already know and so on, right? So we want to do something better than that. Um, Another popular method is what is called Pimsleur method. In fact, this was one of the mainstream, one of the method that actually made language learning popular in mainstream applications in 1960s. This is actually based on two ideas. So it comes up with some kind of a scheduling heuristic, but based on very two important ideas. Right. The first idea is that what is called spacing effect, that the cards should be spread out over time instead of putting them next to each other, right? So you basically, if you have 5 interactions with the student, you should rather spread them over time instead of just showing them next to each other. That's very simple, intuitive idea. And the second is what is kind of interesting, coming from really cognitive science, is called lag effect. It's saying that the gap between two displays should increase over time, right? So basically, you should somehow over time gradually increase this gap. And if you would apply this Pimsleur method on those 5 concepts, then your schedule would look something like this. Just for illustration, I've shown here the schedule for A, right? So what you see here is the gap is kind of over time increased, right? And again, for C, you can see the gap is increased over time, right? And this has been very, very popular method over decades. Now, one of the key limitation of this method is that this method is non-adaptive, right? It fixes the schedule before the learning even starts. The schedule is already fixed. And it basically ignores how learner is doing. So what if learner is actually not able to do certain concepts correctly, or if they already know certain concepts, right? You want to somehow focus on concepts which are perhaps learner is finding it hard instead of concepts which learner already knows, right? This method wouldn't do that. And next comes to one of the more modern version of Pimsleur method is called Leitner system. In fact, this is a variant of this method was basically what was used in Duolingo's early work, as kind of mentioned in some of their works, right? So the main idea is to take the Pimsleur method but make it more adaptive. Now, what would adaptive actually means? It means that if student is doing it correctly, you keep on increasing the lag. But if student makes a mistake, you again reduce the lag. Okay. So if student is always doing correctly all the concepts, this is going to behave exactly like Pimsleur method, right? So this is just the same schedule that I showed on the last slide. So here the schedule, basically the lag is increased from 1, 2, 4, 8, 16. So that's kind of increasing at exponential intervals. The key idea is if student makes a mistake on a particular concept. So what you see on the top right here is that if student makes a mistake on particular concept, the lag for that is again reset back into the original, right? So here I'm showing this example for A and C, on schedule 2. So C is behaving as before because student is always making no mistakes on this. So green means no mistake. Whereas for red, so see, whenever student makes a mistake on red, we don't increase the lag effect. And when student does it correctly, we increase the lag effect, right? So basically lag effect increased, but at some point, then again, student make a mistake on A, then the lag effect decreased. So that's kind of really an adaptive schedule. Now, one of the key limitations of this work is that there is really no way to analyze the schedule. In the worst case, this could end up doing very bad. So what we have been doing in our work is really kind of how can we design a schedule for which we can give formal guarantees before we even deploy it with real world students, right? So that's basically kind of the thing we're going to look at. But before I go to next slide, so there is a question here. Do models usually take the type of assessment into account? No, student has a knowledge about vocabulary, can match a word. Yes, so I think this is a very good question. This goes to the point that I was saying. It doesn't have to be 0 or 1, right? So let's say student made a typo. So student knows it, but basically wasn't able to spell it correctly, right? So you could actually incorporate more of these richer signals into your teaching algorithm, right? So in fact, to make most of this practical, you need to incorporate more teaching, richer teaching signals. For instance, the time it takes if there was a spelling mistake, and so on. Right. So that's a very good question. So now, again, I'm going to follow those three different components. What we have set up so far is basically the kind of the interaction between student and teacher, right? We have set up the kind of the formal representation. We have n concepts, capital T time steps. Now, before we actually go into designing teaching algorithms, we need a model of the learner, right? So model of the learner is very important because that's what we're going to optimize. And here in this case, we're going to look at a model called half-life regression. So this is actually a model which was introduced by Duolingo research team back in 2016. It's a very interesting model specifically because it allows you to learn these parameters from large data sets that they have accessed, right? So let me give you kind of spend next 5 minutes explaining what this model is. And this would require a bit of notation here. And the basic idea is as follows, let's say, let us denote the history of interaction with the student with X and Y. So, right, these are all the concepts that were given to the student, and Y1 to T are all the responses that we saw from student. And for X, we also denote a timestamp, which was the last time step when it was actually taught, which is L of XT. And what we are really interested in is this some notion of mastery, H of XT, like what is really the mastery of student at time T about concept X, right? You would now actually see that this has some connection with also Bayesian knowledge tracing, and it also has some connection with back to part one computational model, right? So that's kind of what I meant is really we are looking at some kind of intermediate model which allows us to reason about learners mastery about skills, but it's also a bit more fine grained. You can actually optimize these models. I'll tell you what does fine grained actually mean. So this model is actually quite nice because it's actually a model which would say what is the probability that if you would ask a particular question X at some time in future tau to the learner, what is the probability that they would be able to answer it correctly? Okay, so this formula might look a bit complex, but let me jump to the next slide to actually show you what this actually means. So this is basically what HLR model really is. So what this says is that learner has some mastery about a skill, which is denoted by H of X. H of X, for instance, could be 5. Okay, and the meaning of 5 is that if you look 5 steps into future, what this means is that learner's probability would be about 0.5 to answer that. So learner's probability is decaying at an exponential rate, and the rate actually depends on this mastery or half-life denoted as H of X. Okay, so that's basically the main idea here, but it's basically an exponential for getting up, right? And now the other important thing in the learner model that we need is how H of X or how the mastery is going to evolve over time. And this is captured by two parameters here. The first is if learner does solve the exercise correctly, then there is a parameter that H of X is incremented by A of X. If learner solves the exercise incorrectly, then H of X is incremented by B of X. Okay. Now this is very much similar to the BKT model here in a way, right? We had some probabilistic model of how learner is going to evolve over time. One nice thing here about is that this also gives you kind of idea about how learner is going to act in any time in future, right? And it has this memory component built into it. So that's about learner model now, right? Now we have these three different components. Now we come to designing a teaching algorithm for this particular learner model, right? And again, I'm gonna basically set up an optimization problem from here. One important thing to note here is that in part one, we used optimization techniques to actually compute optimal teaching set. In part three, we were not able to do that because those cognitive models were a bit too complex to be able to reason about future. Whereas this is kind of a model which is not too complex, not too simple, and we actually going to solve it through some optimization problem to come up with an optimal schedule, right? don't worry about details in next few slides, because I think it's easier to understand this when you actually would read the whole paper. So I'm going to just give you some quick concepts about this in 5-10 minutes, but all these details are actually in the paper, which you can read in full detail. Right now, to actually come up with an optimization problem, one important thing is, what does teacher actually care about in terms of optimizing, right? And there could be different utility functions we care about. One utility function could be, what would be the learner's retention about all the concepts at the very end of the teaching phase, right? So that would be one way objective. Other objective could be, what is the learner's retention about all the concepts throughout the teaching phase, right? So the problem, the way we set up is basically learners retention about all the concepts throughout the teaching phase, and that's kind of denoted as some kind of area under the curve, right? So what this is basically saying is, at any time for any concept, what is the probability that learner would be able to recall that concept correctly, right? So this is essentially the objective that we optimize. And what we are really interested here is designing a teaching policy which would say, given this history of concepts and responses, this is the next concept that I want to give to the learner, okay? And the way this optimization problem is phrased here, a lot of mathematical details are somewhat hidden, but basically what we want to do is come up with an optimal policy which would be able to map this history into the next concept, okay? Now, this is a lot more complex optimization problem compared to what we saw in part one. You know, in part one, we were just doing, okay, what is the sequence of data points we should select? Whereas in this optimization problem, it's a sequential problem because it's really a policy you have to learn, mapping from history to the next item. And it's stochastic, right? Because learners' responses, wise, this is a stochastic function, right? So this HLR model gives you a probabilistic function of how learner is going to respond. So the whole optimization problem is sequential and stochastic. So it's a lot more complex problem. As I mentioned also in part one, the original very simple problem is also already NP hard, and this is actually a more generalized variant of that problem. It has also the same complexity of NP hardness. What we actually show in our work is that you can actually solve this problem, design teaching algorithms with some kind of approximation guarantees. Okay, I'm not gonna give you this in full details, but basically, let me just skim through the slides so you can then refer back those in paper. What we do in our work is really, given this optimization function and given this objective function, we basically design some kind of algorithm for the teacher that would basically come up with this policy. And the next step that goes into doing this research is basically now saying, what can we say about this algorithm, right? How well it would perform before you even do this testing? Can we give some kind of formal guarantees? And the way to go about this is then goes really mathematical, and kind of this is something where kind of if you're doing research as a PhD student, right, then you would basically be working on these kind of problems. You would really try to understand, what exactly are the properties of this mathematical function, and how well this algorithm that we have proposed is going to solve it. And then we have kind of some really formal guarantees about performance, right? These are formal guarantees in a way, doesn't matter what happens, this is the guaranteed performance of the learner. Okay, so I'm skipping through those details, but let me now kind of try to close that loop, right? So what we have seen so far is three different components. We have a teaching algorithm. This teaching algorithm, we have proven some formal guarantees, and then we're going to do experiments on the simulated learners, right? So that's always the first step before doing the final experiments. The experiments on simulated learners basically means that we're going to use this HLR model as a proxy of the learner, right? So we basically just going to simulate a learner who is going to behave similar to this HLR model, right? And we're going to use a lot of these different algorithms to be able to then test and compare our algorithms. Now, for the simulation, you also need to fix some parameters. And for our simulation, what we did was we took 15 concepts. Half of them were easy concepts with parameters 10 and 5. Half of them were difficult concepts with parameter 3 and 1.5. I'm not specifying the full parameters here for the HLR model, but basically in simulations, you always fix certain parameters. So then you can test your algorithms, and you can also test your algorithms robustness across different parameters. Okay, and we would measure their performance on two different metrics. One is the objective function that we actually optimized, this kind of area under the curve throughout the teaching phase. One is their recall in the very end, right? So after the teaching phase is finished, how are they going to perform at the end of that? So I'm going to show you just some quick plots here. So first is how does our algorithm is denoted in this GR, the green here. This is the greedy policy that we designed. RD is the random policy. RR is the round robin policy. LR is based on a variant of Leitner's system that I showed you earlier. Okay, so these are basically four different algorithms. I showed you that LR actually is one of the state of the art adaptive scheduling techniques, but it doesn't come with any formal guarantees. And this is basically a way to look at this now, right? So second slide, the second plot here is kind of interesting. So on the x-axis, we are increasing n here, right? As you increase n, the problem becomes more and more complex, right? So you have to teach more concepts for a fixed time window of 60, right? So in the second plot, t equal to 60, and when n is 30, we basically have just 60 slots to teach 30 concepts. Very hard problem, right? All algorithms kind of perform that. But what you can see is that our policy still has substantial gain and kind of over top of these baselines, right? And then we also look at some other metrics like recall in the future. That is some metric that we might be interested in real world user studies, for instance. Right, so these are simulated learners. These are actually experiments that we perform on a machine. Now, I told you in the beginning, one should not really try to take away from there and stop here, because it might be that we have a very wrong learner model. Even if you get good simulation results, it might be that the teaching policy actually is not going to perform well on human learners, right? So that's where it comes to about completing the loop, right? So for our work, for instance, we developed these language learning platforms. These are mostly small platforms that we develop for user studies. We don't basically deploy it at a large scale, more like user study kind of platforms for evaluating our algorithms. And we do that for most of the application-oriented projects, right? So this app basically allows us to do the following kind of study. The whole phase is separated into three phases. The whole session is separated into three phases. One is a pre-quiz phase where we would ask students questions to get their idea about their pre-knowledge. Then there would be a learning phase for 40 time steps. And then at the end, there would be a post-quiz phase where we would test their knowledge about how much knowledge they have gained, right? And the performance that we would show here is basically the performance from post-quiz minus pre-quiz, how much knowledge they have really gained. Okay, so there are still no more questions, so I would keep going here. I think applications in sports, I think we have discussed that, right? So one concrete application would be in these educational simulators for learning to play chess, for instance. These are, I think, very interesting gaming applications where we could use some of the ideas, because there one has to use a right opponent that one should design. And the other is a question about example of complex cognitive model. So BKT model is one example, and HLR model is actually yet another very interesting example, which is a mix of a cognitive model and a cognitive model and a computational model. But you could make those BKT models very complex by just making more complicated dynamic Bayesian network. So the model used in assessment has 125 skills. So it's a very complex model actually used in practice. Okay, so just to give you a quick overview of these user study results, right? So here we recruited 80 participants from a crowdsourcing platform. Is kind of a controlled user study, putting people into different groups, right? We have these 15 concepts and 40 time steps in which we're going to interact, right? And what we kind of reporting here is really the gain in knowledge from pre-quiz to post-quiz for these different students, right? So what you see here is basically this GR policy that we designed not only performs well in simulations, but actually it does perform well in real user studies as well, right? Of course, these are controlled studies. One should not kind of have a big takeaway from these, but this gives a good sign that what we are doing kind of is making some sense here. Then we did also these user studies on another application of teaching people to recognize animal species. So here we took a data set of 50 animal species that we actually handcrafted. And to actually run your policy, you still need some parameters, right? So the algorithm is optimized for these parameters in mind, and then is actually interacting with the real human student to report these numbers, right? And here we have 80 participants per algorithm. And here you see that we report two kind of performances. One is on the all the species, how much knowledge is gained from beginning to end. And then knowledge on rare species, right? This number is higher actually because the pre-knowledge was almost zero. So there's a big gain for our algorithm, whereas random actually is quite low here because random just spends equal time on all the concepts and is not able to basically save budget on the easy concepts, right? So just to get back here, right? So this is basically the second application where we kind of looked at a bit of in a model which is inspired from cognitive model, but also has some kind of a computational aspect, allows you to predict about student, right? And next in I'm not gonna tell you the details of this, but basically the main thing I want to point out here is that um, when you go into more complex applications like gamings, educational simulators, the goal there is a lot more complex because you are teaching something, not just how to take an action, how to basically remember certain things, but you are actually teaching them strategies. You are teaching them how to take a sequence of actions so you could actually win a chess game, right? Or how could you actually drive safely from point A to B without having accident and being able to reach quickly home. So here, what we are using is a lot more focused on reinforcement learning. One of my colleagues, Goran, is going to actually teach a lecture on multi-agent reinforcement learning. And here, in these more complex application settings, we are actually using more reinforcement learning style learner models. So a lot of our recent work is actually on more of these complex settings, which are inspired from coding, gaming applications like chess, or educational simulators, where the goal is to teach a strategy, right? That's a lot more complex than teaching them a particular rule. Okay. Now, that brings me back to this basically three different parts, right? So what we have looked at in this lecture is really the left viewpoint of information theory models of teaching, which allows us to understand the teaching complexity and how does it compare to learning complexity. Then you have the right extreme, which is about cognitive models of learning and teaching, which are models useful for real world applications, with the limitation that sometimes they are too generic and complex and might not allow you to design teaching curriculums. And then there's a space in between, which is about designing models which are not too generic, not too abstract, just of the right complexity suitable for the application at hand. And so that's where most of my research group is working on, kind of in the box in the middle here. And so in general, machine teaching is basically a space with a lot of interesting research questions, a lot of interesting applications, and a lot of interesting connections with other parts of problem settings, right? Basically on theory side, really understanding the communication complexity, on more applications side, really understanding the cognitive process of human reasoning. And so there is a lot of interesting work that needs to be done here. So I'm just going to conclude this lecture with a link to our group webpage, some publications, so some of the things that I presented, especially this part 3 of the lecture about designing schedules for language learning. This is a recent paper that you should look at. And this is my contact information. Just feel free to send me an email, right? I'll be very happy to know if you're interested in some of the topics, if you're interested in knowing more what problems we are working on, or if you have some ideas that you would like to exchange, or you have some questions about the lecture, just feel free to send me email. with that, I would conclude. I'm going to look at Slido again. So I guess we have one question of any applications in sports, and I think that is something that I mentioned, right? So the third, in part three, if you go to more complex application scenarios where you're teaching strategies, chess is, I think, very interesting application domain that we have been reasoning about. Where we want to teach some strategies to students. So teaching to play chess, or teaching to do coding, or teaching to play learning to drive. These are kind of more complex applications that I would fall in this regime of sports here. Any further questions on Slido? Okay, I guess that's it for now. I'll just wait for a few more minutes in case some other questions pop up in next few minutes. Okay, I'll keep the slide with the contact information here. We can also have more discussion on Slack. I'll be checking your messages. So later in the day, I think that would also be a good way to keep in touch. So there is a question, who is a better teacher, human or machine? So I would actually say we are not there yet to beat human teaching performance, right? So I think that's kind of more of an inspiration or benchmark we would like to get to, or get more inspiration from human teacher. And perhaps one interesting thing to keep in mind is that, right, the goal is not really to replace human teaching process, but perhaps later on there is some online teaching algorithms along with the help of human interventions, right? That might be the way to go into future. But at this point, we are still far away to get anywhere close to a human teaching process. Okay, so that's it for now. Yes, please feel free to ask more questions on Slack later on. Thank you very much. Bye bye.
Thank you.
Okay, so Maria, so should I guess I can stop here, right?
Yes, right. Yes.
Okay, good. Thank you so much.
Thank you too.
I will check message on Slack if students have more questions.
Okay. Have a
Bye.
nice day. Bye.
You too.